Because integration is the reverse of differentiation, if we want to integrate our usual functions from a2, we need to know how to differentiate them. I'll go through these one at a time, see how many you can get. If y is equal to sine x, then the derivative will be cos x. If y is equal to cos x, then the derivative will be minus sine x. If y is equal to e to the x, the derivative will be e to the x, same thing. If y is equal to ln, natural logarithm of x, then the derivative will be 1 over x. If y is equal to tan x, the derivative will be sec squared x. Trickier one, if y is equal to a to the x, then the derivative will be a to the x ln of a. So if we're integrating, why did we bother finding the derivatives? Because if we know that the derivative of sine is cos, then this means if we're going backwards, the integral of cos will be sine. If the derivative of cos is minus sine, then the integral of sine will be minus cos. If the derivative of e to the x is e to the x, the integral of e to the x is e to the x. If the derivative of ln x is 1 over x, then the integral of 1 over x is ln x. If the derivative of tan x is sec squared x, then the integral of sec squared x is tan x. And if the derivative of a to the x is a to the x natural log of a, then the integral of a to the x natural log of a will be a to the x. So a few notes about these. The coses and the sines go in a cycle. We know that sine differentiates to cos, which differentiates to minus sine, which differentiates to minus cos, which differentiates back to sine. And if we do the whole process but backwards, sine of x will integrate to minus cos of x, which will integrate to minus sine of x, which will integrate to cos of x, which will integrate to sine of x. Another thing to note is that we actually need a modulus sign around the x in the natural logarithm, because the natural logarithm cannot be negative, but 1 over x as a function is negative when x is negative. The final thing to note is that all of these integrals, of course, need a plus c. Let's look at two examples. Example 1, we're going to be integrating 3 sine x minus cos x minus 1/3 e to the x. From above, we know that the integral of sine is minus cos, so this is going to be 3 lots of minus cos, or minus 3 cos. Minus the integral of cos is sine, and there's only one of them, so minus sine. And as we know, e to the x doesn't change, and as always, don't forget your plus c. In example 2, we've got the integral of 1 over 2x plus 1 over 2 cos squared x. Not quite as easy this time because the 1 over 2x isn't quite how we want it. So we first need to rewrite this as 1 over 2 lots of 1 over x, because now this is something that we know how to integrate. Similarly, we can do that for cos. So 1 over 2 times by 1 over cos squared. You need to know your second year identities here because 1 over cos squared is sec squared. And that's good because that's one of the integrals that we saw above. So let's integrate 1/2 times by, what's the integral of 1 over x? It's ln modulus x, plus another half times by, what's the integral of sec squared x? That's tan of x. What are we missing? Plus c. Okay, over to you. Can you find the integral from 1 to 2 for e to the x plus 2 over x? Is it option A, B, C, or D? Pause now, and I'll reveal the answer in 5, 4, 3, 2, 1. The answer is D. On to question 2. The integral from minus pi over 4 to pi over 4 of 1/2 cos x minus 2 sin x dx is a over b root c. What is the value of a, b, c? Is it 4, 3, 2, or 1? Pause now, and I'll reveal the answer. The answer is A, 4. Now for more derivatives. Using the chain rule, what is the derivative of sine of 2x? That should be 2 cos 2x. What is the derivative of cos of 3x? That should be minus 3 sine 3x. What's the derivative of tan of 1/2 x? That's 1/2 sec squared 1/2 x. And what's the derivative of e to the 5x? That's 5e to the 5x. This will help us work out any integral of the form cos with a constant times by x, or sine with a constant times by x. What would the integral of cos of 2x be? Well, if there were a 2 here, we'd know this integral, it would be sine 2x. But we can't just put a 2 there because it would change the question. But if we put a half on the outside, we're all good. Half times 2 is 1. We've not changed anything. But now we know the answer to be 1/2 lots of sine 2x. We can do a similar thing for the integral of sine of 3x. If there were a minus 3 here, then we'd be very happy. But there's not. So let's times by minus 1 over 3 on the outside. Those two numbers times together to give 1. We've not changed anything. But now we know the answer is minus 1/3 lots of cos 3x. Let's do the same thing for sec squared. If we want the integral of sec squared 1/2 x, if there were a half here, we could make light work of it, but there's not. So let's put a 2 on the outside, and now you can see we've not changed anything, but we know the integral to be 2 lots of tan of 1/2 x using our derivatives on the left hand side. And finally, if we wanted to integrate e to the 5x, then we could only dream of there being a 5 next to the e. All dreams can't come true, but let's put a 5th on the outside. Now we know the answer to be 1/5 e to the 5x, with a nice big plus c on all the integrals there. In a similar way, if k is any constant, then the integral of sine will be minus 1 over k cos kx plus c. The integral of cos kx will be 1 over k sine kx plus c. The integral of e to the kx will be 1 over k e to the kx plus c. And the integral of sec squared kx will be 1 over k tan of kx plus c. You'll notice the pattern 1 over k repeating itself for all of these common A2 integrals. If you can commit these to memory, great, do so. If you can't, do so anyway. Now for some examples. Firstly, we're going to integrate this lovely expression. So we recognise the rule. We see the sine, we know its integral is going to be minus cos, but divided by the k, which in this case is 3 over 2. The 3 over 2 at the front is going to stay where it is, because that's just constant. So we're going to get 3 over 2, lots of minus 1 over the k, which is 3 over 2, lots of cos 3 over 2x. We'll simplify that in a second. Let's work on the second term. We'll have minus 2/3 from here, that's the constant. Then we're going to have times by 1 over k. What's k in this case? 2/3. Lots of sine 2 over 3x. If we then simplify this, we're going to get minus cos 3 over 2x, and we're going to get minus sine 2 over 3x with the plus c at the end. If you're ever unsure, then you can differentiate this and you can check it's the same as what's in the integral. Example 2 is 4 over cos squared 2x minus e to the minus a half x. We see a cos squared in the denominator. We turn that straight away into a sec squared. We know how to integrate sec squared is tan, but the constant 2 tells us to do 4 lots of 1 over k, k is 2, tan 2x. Now we get to the e, minus 1 over k, in this case k is minus 1/2, and then the power of e stays the same. 4 times a half is 2, and if I cancel out the 2 negatives and bring the 2 to the top, this is our final answer. Again, if you really want to, differentiate this and see if you get the same. Right, 2 more questions for you to do. Here's the first. Pause now, and I'll give you the answer in 3, 2, 1. I'm not going to bother saying that out loud. Check if you've got it right. And question 4 is this. You will need to use a bit of trig to help you get this one. I'll give you the answer in 3, 2, 1, 0. Well, there you have it. That's how you integrate normal A2 functions. Be sure to memorize that list so you'll be ready to integrate by parts next.